Hi guys, so today we're going to discuss about mathematical language and symbols, but we are now going to focus about variables. Before we proceed, let us define what a variable is. It is commonly represented by a letter like X or Y. For actually, you can make use of any letters in the alphabet. You can make use of A, B, C, D, and so on. Now we use this symbol for a value that we don't know yet. That's why we are trying to represent it with a letter. It allows us to give a temporary name to what we are trying to solve or to what we are trying to compute for us to discover what are the possible values. All right. Now let us use the variables to rewrite the following sentences formally. Let's have letter A. Are there numbers with the property that the sum of their squares equal to the square of their sum? So this is the question or the sentence that we are going to rewrite using variables. Now, remember that we can see here the word numbers. So it's plural, meaning we are going to use two variables or two letters. So we can write it as, are there number such that, or are there number X and Y that would represent the two numbers with the property, remember that we have here the word sum or the term sum. So we use the symbol for sum, which is the addition symbol, and it says here that the squares of the two numbers, so the square of X and Y, so we have X squared and Y squared, is equal to or equals the square of their sum. So we are going to add the two numbers X and Y, and then we are going to square that. So that's how you rewrite that sentence using variables and mathematical symbols. We can also write this as, are there numbers X and Y such that X squared plus Y squared is equal to X plus Y squared, or quantity squared. All right. Next, given any real number, its square is non-negative. So there is a real number, and if you're going to square that real number, it is a positive number. It's non-negative. So how are we going to rewrite this sentence? Okay, so we can rewrite this as, given any real number, we make use of small letter r. Remember that in variable, we make use of the small letters. Because if we are going to use the capital letters, that denotes for the sets. All right? So we make use of small letter r here for real number. Anyway, we can use X, we can use Y, but in this example, we are just going to use R. Okay? To represent. So R squared is non-negative. We can also write this as, for any real number R squared is greater than or equal to 0. We can make use of this symbol as well because it says here non-negative. Now the numbers that are 0 is non-negative as well. Now the numbers that are greater than 0, so we have 1, 2, 3, 4, and so on. All right. We can also make use of 0. So from 0, 1, 2, 3 up to infinity. We can also write this one as, for all real number R squared is greater than 0. So in this example, the difference is just you use the word any, and this solution we make use of the word all. Right? But the thought of this is the same with this one. We just translated or rewrite it in the following sentences. Okay, some important kinds of mathematical statements. We have the universal statement. It says that that certain property is true for all elements. Now, we can say that it is a universal statement if you see the words or the phrase for all. Sometimes it uses for every or all or for each. So that is universal statement. Remember that it is true for all elements. Let's have an example. All positive numbers are greater than 0. All positive numbers are greater than 0. So we all know that 1, 2, 3 are greater than 0 and it is positive. Right? So that is a true statement for all elements. So that is an example of universal statement. The next one is the conditional statement from the word condition, meaning a conditional statement has conditions, right? So it says if one thing is true, then some other thing also has to be true. So we make use of the phrase if then, or the words if then in the statement. Say for example, if 378 is divisible by 18, then 378 is divisible by 16. So if one thing is true, so 378 is divisible by 18. So if you are going to divide 378 by 18, you will get a quotient which is a whole number. Then 378 is also divisible by 6. Now, why can we say that 378 is divisible by 6? Because 18 is also divisible by 6. That's why we can also divide 378 by 6. So it is true in this statement and it is also true in this part, right? Okay. We also have the existential statement. It says that there is at least one thing for which property is true. So at least one thing that is true. Let's have, there is a prime number that is even. Okay? So it is an even number and it is also a prime number. So we all know that the only number that is prime and also even is 2. Okay? So there exists a number that is both prime and also an even number. So that is existential statement. Now we also have the universal conditional statement. What is universal and conditional statement? So a statement that is both universal and conditional. Obviously, it is universal and conditional statement. So let's say, for example, for all animals A, so we make use of the variable A here. If A is a dog, then A is a mammal. So in this part, it makes use of the phrase for all. So therefore, it is a universal statement. If A, so meron tayo if and then, so that is a conditional statement. That's why it is called universal and universal conditional statement. Now, this universal conditional statement can be written in ways that make them appear to be purely universal or purely conditional. How? Let's take this one. If A is a dog, then A is a mammal. So, if an animal is a dog, then the animal is a mammal. So remember that if you can see if and then there, so that is conditional statement. So this is purely conditional statement. Even this statement, this is purely conditional because of the word if and then. Alright? We can also rewrite it this way. For all dogs, A is a mammal. For all dogs are mammal. So remember that in these two statements, these are purely universal. So universal conditional statements can be both universal and or can be written purely as universal or purely conditional statements. All right? We can also rewrite this one. So let's have these examples. For all number x, if x is a non-zero, then x squared is positive. So this statement, we are going to fill in the blanks to rewrite the following statements. So if a real number, remember that if a real number x, if x is a non-zero, then x squared is positive. So there is a real number x, and if you're going to, and if that number is a non-zero, and if you're going to square that number, you will get a positive answer. So if a real number is non-zero, then its square is blank. Its square, what will be your answer? I will give you time to answer that later on. Maybe I'll give you around 2 to 3 minutes. Let's have this one. For all non-zero real number x, blank. If x blank, then blank. The square of any non-zero real number is blank. Okay, I'll give you time to answer. You may pause the video for a while and then try to answer it, and then you may get back to this video when you're done. All right? Okay, now let's try to answer. If a real number is non-zero, then its square, okay, your answer should be is positive. Next, for all non-zero real number x, what's your answer? All right, so x squared is positive. Next, number 3, if x, okay, is a non-zero real number, then x squared is positive. Now lastly, the square of any non-zero real number is positive. So remember or take note that all your answers comes from the original statement. All right? The same thought. You just have to fill out or fill in the blanks. All right? Okay. We also have universal existential statements. Now, what is universal existential statement? These are statements, statement that is universal because its first part, so the first part says that a certain property is true for all, meaning that is universal. And its existential part, or the second part, asserts the existence of something. So the first part is true for all, that is universal. And the second part, there is an existence of something, or there is an existence of a certain number. So that is existential statement. So let's say, for example, every real number has an additive inverse. So we use here every that is commonly used for universal statement, and then there exists an additive inverse for every real number. So therefore, there is an existence of an additive inverse. So that is for the existential statement. Now, we can write this as all real numbers have additive inverses. So the same thought. We make use of the word all here. So this is universal and this is existential. We can also rewrite this as for all real numbers R, there is an additive inverse for R. This time, we make use of the variable R to represent the real number. Okay? So again, we use for all, so that is universal, and there is an existence of an additive inverse for every real number, so that is existential. Right? We can also rewrite this as for all real numbers R, there is a real number S such that S is an additive inverse. So this time, we use two variables. We represent R for real numbers and we represent S for additive inverse. Again, there is for all for universal and additive inverse, the existence of the additive inverse that is for existential. All right? Okay, now let us rewrite this one. Fill in the blanks again. Every pot has a lid. All right? So I will give you 3 statements. You fill in the blanks. You may pause the video again and then you get back to the video once you're done answering. All right. So all pots have lid. All right. I hope you got it right. Next, for all pots P, so we make use of the variable P here to represent pots. And this one, this is universal. There is blank. So your answer should be a lid for P. So for all pots P, there is a lid for P. So therefore, there is an existence of a lid that is universal. I mean, that is existential. So next, for all pots P, there is a lid L such that, so your answer should be L is a lid for P. So we make use of 2 variables here, P and L. L denotes for the lid and P for pots. Again, we make use of for all here, that is universal, and the existence of a lid for every pots, so that is existential. Now, the last one, we also have existential universal statements. Existential universal statements, these are statements that is existential because its first part asserts that a certain object exists, and is universal because its second part satisfies that a certain property for all things. So there is a property for all things and it is true. All right? Okay, again, existential, and the second part is universal. Let's have this example. There is a positive integer that is less than or equal to every positive integer. So there is an existence of a positive integer, and in every integer there is that is less than or equal to every positive integer. So we make use of the word every here, meaning that is universal, and there is a positive integer that exists, so that is existential. Right? So let us rewrite this. There is a person in my class who is at least as old as every person in my class. Again, there is a person in my class who is at least as old as every person in my class. Okay, so I'll give you maybe 2 minutes for this one, or maybe less than 2 minutes. Again, you may pause the video for a while and then try to answer this one, and you get back to the video once you're done. Okay, so some blank is at least as old as blank. Okay, so we have some person in my class is at least as old as, all right, every person in my class. So this one, that is for universal. The second part, the first part, some person in my class. So there exists a person in your class that is at least as old as every person in your class. All right. So there is a person P. We make use of the variable P here to denote person in my class such that P is at least as old as every person in my class. So this is for the existential part, and this is for the universal part. Okay, so do you have any questions? Well, if you have, you can find me at, you look at the screen, that's where you can find me. And thank you for watching.